All right, so chapter 10 is going to be building on what we covered in chapter 9. Again, working in sort of these stacks of concepts in terms of how the chapters work. Chapter 9 was sort of like a new foundation for chapter 10. And I believe chapter 11 builds on it as well. So we talked about valence electrons and how valence electrons determine how things or how atoms interact and how they form molecules, why they form molecules. We can also use that knowledge of those valence electrons and the way that molecules bond to figure out the structures of proteins. So this protein over here looks weird, like a long bendy worm in 3D space, is actually made up of chains of molecules. So it's a super huge molecule, and it folds in super weird ways, but those can be predicted based on bonding theories. So the structure of this molecule let researchers develop potential drugs for HIV to block this and inhibit the virus. So bonding theories predict how atoms bond together to form molecules. They predict what combinations of atoms form compounds and what combinations don't. You can predict formulas of compounds, explain the shapes of molecules, and which in turn determine many of their physical and chemical properties. So the simplest one, and the Lewis dot structure is based on this, is Lewis theory. And we can use that to make sort of quick, everyday predictions about molecules. So in Lewis theory, the valence electrons of main group elements are represented as dots surrounding the symbol of the element. So if we wanted to take a molecule like, let's just do oxygen. Yeah, oxygen on the periodic table. If you want to figure out how many valence electrons any main group element has, so it's the S block, which is the ones on the left. Oops, cursor's over here. S block is these two columns. P block is these guys over here. You can just use the column number, and that tells you how many valence electrons it has. So oxygen is in column 6A, or 16, so it has 6 valence electrons. So come back up here, so this is oxygen. So we draw little dots around it, 1, 2, 3, 4, 5, 6. So oxygen has 6 valence electrons. In a Lewis structure, you would draw it like this. Also called a dot structure. So again, the group number of the element tells you how many valence electrons. So oxygen is in 6A. Of course, it's the example on the next slide. So electron configuration of oxygen, which we just did. Again, oxygen is in column 6A, so it's going to have 1, 2, 3, 4, 5, 6. We generally draw those electrons around it in pairs. Oh, sorry, electron configuration. The electron configuration for oxygen, go back to the periodic table. So we want to figure out the electron configuration. Remember, we can use the periodic table as a guide. The first one is 1s. So 1s is hydrogen and helium. And then we move down a row to 2s, which is lithium, beryllium. And then 2p, where we'd have oxygen is, 1s1, 1s2, 2s2, and then 2p4, because oxygen's the fourth element in the p block. So this would be 1s2, 2s2, 2p4. And again, if we wanted to identify the valence electrons from an electron configuration, it's all of the electrons that are in the highest principal quantum shell. So here 2 is our highest principal quantum shell. That's what that first number is. And so we've got 2 electrons here in 2s, and 4 electrons in 2p, for a total of 6 valence electrons. So we just write oxygen in our Lewis structure and then put 6 electrons around it. Again, usually 2 electrons to a side. We'll get to why that's important. So each of those dots represents a valence electron. We place the dots around the element symbol with a maximum of 2 per side. The exact location is not critical. So you could fill the dots one at a time first and then pair them, or you could pair them. But we fill the dots in singly first and then pair them. It's important to follow this convention. Oh, you don't need to worry about that. That's mastering chemistry. Atoms with 8 valence electrons are particularly stable. Again, when we're talking about electron configurations, we can use this fact that 8 valence electrons is particularly stable to predict why groups 1 and 2 have +1 and +2 charges that they form because they want to lose electrons, and then why groups 6a and 5a want to be 1- and 2-. So those 8 dots is called an octet. Oct being the prefix for 8. Okay, so if we're going to write the Lewis structures for the first 10 elements, how many valence electrons does hydrogen have? Just 1. How many does helium have?
1 or 8.
Oh, no, yeah, 8 is the exception to that.
Oh, okay.
Helium is the exception to the rule of using the periodic table. So yeah, helium has 2. And then lithium, 3. Beryllium has 4. So filling these in singly first. And then boron. Then we compare them. Valence electrons. Valence electrons. Lithium only has 1 valence electron because the electron configuration for hydrogen is 1s1. For helium, it's 1s2. For lithium, it's 1s2, 2s1. So only that last electron is in that highest principal quantum shell. So for beryllium now, we have 2 valence electrons again. How many valence electrons does boron have?
Two.
3.
Oh, 3. Okay.
So it is in column 3A.
Okay.
So boron has 3. Carbon has 4. So we go back. Nitrogen, 5. Oxygen we already looked at. Oxygen has 6. Fluorine has 7. And neon? 8.
Okay.
Yeah. Helium's the only one that doesn't have the same number of valence electron as its column number.
2.
Only 2. Yeah. Oh. So helium is stable with a duet. Yeah.
Question, does it matter, like, as far as putting the electrons, where you put
as long as they're all on, it's only 2 electrons per side. So that is important. Aside from that, it doesn't matter how you arrange them. So like for boron, whoops, like it could have been like this, or like this, or if you like had something like fluorine, it could have, like the one lone electron could have been on the side there, or top, or on the left. Yeah. Any other questions? All right. So in Lewis theory, a chemical bond involves the sharing or transfer of electrons to attain stable electron configurations for the bonding of atoms. So again, this goes back to the electron configurations where everything's trying to get 8. So electrons can either transfer electrons in ionic bonds, or they can share electrons in covalent bonds. There are a few that are exceptions to this, but in general, the octet rule is we're trying to trade or share electrons so that all of the atoms involved in a molecule have 8 valence electrons. Hydrogen, lithium, and beryllium are exceptions. They only follow the duet rule. And boron and aluminum, I guess it would be the hex set. Boron and aluminum will form compounds that only have 6 valence electrons. So those are the only exceptions that we're going to have. All right, so we read the Lewis structures for magnesium, sulfur. The magnesium, sulfur. How many valence electrons does magnesium have? So over here. 2. Just 2. So if we go back, put those valence electrons around magnesium. And sulfur has? 6. Yeah, 6. It's over here in column 6A. So it has 1, 2, 3, 4, 5, 6. All right, now what charges generally, or actually these are the only charges they form, what charge does magnesium form?
2+.
2 plus, and sulfur is?
2-.
2 minus. So if we have magnesium 2 plus, sulfur 2 minus, it's kind of what these are going to end up at, because magnesium wants to get rid of 2 electrons. Right, if magnesium's here, it needs to lose 1, 2 electrons, and it'll have the same electron configuration as neon. And sulfur wants to gain 1, 2 electrons to have the same electron configuration as argon. So if we take these electrons from, just in a different color, take these electrons from magnesium that it wants to get rid of, and we give those to sulfur, then sulfur now has the electron configuration it wants, an octet. Magnesium loses those 2 extra electrons, which opens up the electron shell underneath. And so we can form a bond between those 2. Oops. Can you? Okay. So those 2 electrons become a bond, and this bond is worth 2 electrons. This is an example of an ionic bond. If you remember nomenclature, this is also an ionic compound because it involves a bond between a metal and a nonmetal. So again, when metals bond with nonmetals, electrons are transferred from the metal to the nonmetal. And they transfer as many electrons as are needed to get the metal to its octet and to get the nonmetal to its octet. And in doing so, the metal becomes a cation and the nonmetal becomes an anion. And actually, for these compounds, they don't really form a bond per se, but they stick together because now they're opposite charges, kind of like opposite magnets. So that's why it results in an ionic compound. So in Lewis theory, we represent this by moving those electron dots from the metal to the nonmetal. So we write the Lewis structure for potassium and chlorine. Again, how many valence electrons does potassium have? Just one. And chlorine? 7. So one valence electron for potassium is going to be 1 dot. Actually, I'm going to draw it on the other side. And then for chlorine, you have 1, 2, 3, 4, 5, 6, 7. So while it doesn't really matter where that single electron on chlorine is or the single electron on potassium is, it's a little bit more convenient if you put them on the same side. Because what we're going to get is the transfer of this electron from potassium to chlorine. And then we're going to have potassium with a plus charge and chlorine with a minus charge. So that gives chlorine an octet. It's happy. Now it's got the number of electrons that makes it the most stable. And potassium loses its only valence electron. So it opens up the valence shell underneath, which is already full. The Lewis structure of an anion is usually written in brackets with the charge in the upper right corner outside the brackets. So really you draw, if you had chlorine as an ion with an octet, kind of make it more clear that that charge is not, or to make it more clear that that negative is the charge, put it in brackets. Again, don't worry about mastering chemistry. All right, so what about sodium bromide? How many valence electrons does sodium have?
1.
Just 1. And bromine? 7 again. So we go again, 1, 2, 3, 4, 5, 6, 7. So the Lewis structure for the compound sodium bromide is going to be Na plus, and then really it should be that next to Br in brackets. Yeah.
So you're adding an electron from Na to bromine, correct? So
Mm-hmm.
that's why. Okay. Because I know, like the other time, right? You put like a bond, right?
I put like a bond, yeah.
So we didn't have to. Never mind. I got it.
Yeah. Just move it in steps. because they're not actually connected by a bond, they're stuck together by the opposite charges. Which is why these are called formula units and not molecules necessarily, although I've been using that term interchangeably, because you'll have, instead of just having the one sodium and the one bromine, you'll have another bromine up here, because they're completely transferring these electrons, and another bromine down here, again forming like a 3D grid of sodiums, and there will be sodiums in here too. So they all just clump together. And these are just ionic compounds. We talk about molecular compounds, those exist as independent structures. Yeah. So Lewis theory predicts the correct chemical formulas for ionic compounds. For example, if we have barium fluoride, put a little more space. So we have barium and 2 fluorines now. Actually, maybe I should. Oh, that's fine. I'll leave it like this. So barium has 2 valence electrons because it is in column 2 on the periodic table, just all the way at the bottom here. And then fluorine, again, has 7 valence electrons. So we give fluorine 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. So barium has 2 electrons to give away. If fluorine's the only thing around to give away electrons 2, it has to give away 1 electron to each fluorine. So you have 1 barium giving electrons away, 1 electron each to 2 fluorines. If we had something like aluminum, which has 3 electrons, then we would need 3 fluorines to give those electrons away to. So we go 1 here, 1 up there. So this is why also when you name ionic compounds or you write the formulas for ionic compounds, you match the charges so that they add up to 0. Because what you're really doing is saying all of these electrons from the metals are being transferred to all of these nonmetals. So they're all balanced. So that's why aluminum be AlF3. Good? Questions? Cool. So if we wanted to predict a formula for a compound that forms between magnesium and nitrogen, magnesium and nitrogen. Let's see, how many electrons does magnesium have?
2.
Just 2. And then nitrogen has how many valence electrons? 5. 4, 5. So magnesium wants to get rid of 2 electrons, but nitrogen needs 3. So if we want to balance this, and this is where learning how to pair these compounds up helps a lot, right? So if nitrogen gains 3 electrons, its charge will be N3 minus. If magnesium gives up 2 electrons, it's going to be Mg2 plus. So how many magnesiums and nitrogens are we going to need? Yeah, 3 magnesiums and 2 nitrogens. Because each of these magnesiums is going to be giving up 2 electrons. Maybe I'm going to move that there. Sorry, 2 nitrogens. So if this magnesium on top gives up an electron here and here, and this one also gives one to that nitrogen, and this magnesium can give its other one there, and the last one here. So at the end of this, all 3 magnesiums will have given up both of their electrons, and both of the nitrogens, all 2 of them, will have gained 3 electrons. Which is why the simplest formula unit for this ionic compound would be Mg3 and 2. Can't go any simpler than that because then some of the magnesiums wouldn't be able to give up their electrons and the nitrogens wouldn't get as many. Yeah?
So how did all 3 of them give up? So would it, because since one magnesium has 2, right? So, but there's only 2, I don't know, I'm getting confused. So there's
Mhm.
2 nitrogens, right? So they each has 5, right? 5 electrons?
Mm-hmm. So count up how many electrons we have in the magnesiums total. We got 6 that we want to give away. And then between the 2 nitrogens, they want to gain how many?
2 each, right?
3 each.
3 each, okay.
Yeah, they want to get to 5. Or sorry, they have 5, they want to get to 8. So they're going to be looking to gain 6 electrons also. Does that help? Yeah. So that's ionic compounds. Really has to do with the charges because the charges, they have those charges because it's related to the number of electrons they want to give up or the number of electrons they want to gain in the case of anions. For nonmetals, it's a little bit different because when we bond a nonmetal with another nonmetal, we make a molecular compound. And molecular compounds have covalent bonds. So ionic compounds have ionic bonds. They're completely transferring the electron from one atom to the other atom. In molecular compounds, a covalent bond, kind of like if you're familiar with the word covenant, is like a promise or a share. It's a thing shared between 2 atoms. Each nonmetal will share electrons but doesn't give them up completely. And that's how we get these dedicated bonds. So for Lewis structure for hydrogen, so for hydrogen, if it has just 1 electron, oxygen has 6 valence electrons. 2, 3, 4, 5, 6. If hydrogen wants to have a duet and oxygen wants to have an octet, it's going to need to have another hydrogen around to share electrons with. So instead of transferring those electrons completely away from hydrogen into oxygen, they actually bring these together to form a bond. So we get hydrogen bonded to oxygen. And again, each of these bonds is still 2 electrons. But now those electrons in the bond count for hydrogen and they count for oxygen. So we can count oxygen's electrons now as 2, 4, 6, and 8. And each of the hydrogens just has 2, because all they need is a duet. So we have different names for these electrons. The ones that are left out are bonding pairs, are lone pairs. The ones in the bond are bonding pairs. And they almost always exist in pairs. Actually, really almost always. Otherwise, they're called radicals. So our bonding electrons are shared. So if we have hydrogen again, or H2O, right? These ones are bonding pairs. These ones are lone pairs. Bonding pairs. Actually, let me write pairs. Because it's easy to forget that that line represents 2 electrons. All right, so those are pairs. So these have come up a bunch. The Brinkelhoff. And each of those elements in that acronym is diatomic. So they all exist, Br2, I2, N2, Cl2, H2, O2, and F2. And Lewis' theory explains why this is the case. So if we have bromine, it has 7 valence electrons. And if we have another bromine, with 7 valence electrons, if they each just share 1 electron, we can form Br2, where each of these bromines now has 8 valence electrons, because we can include this the bonding pair in the bond and count those for each of the bromines. So 2, 4, 6, and 8, 2, 4, 6, and 8 on the other side. Hydrogen also exists as a diatomic element for the same reason, right? If each hydrogen has 1 electron, all they have to do is each share their 1 electron, and they can have a duet. And you can do the same thing for any of these Brinkelhoff elements. Let's do another one of these. For oxygen, we've got 1, 2, 3, 4, 5, 6 electrons. And again, oxygen is one of these diatomics. So if we draw out our second oxygen, so if we just share 1 electron between these, that won't get them to 8. But we can actually share 2 pairs of electrons. We can share 2 electrons each. So these will be shared and these will be shared, which results in a double bond. So now instead of sharing just 1 pair, they're sharing 2 pairs of electrons. And so this is 4 total electrons. So if we count up the number of valence electrons that each of these has now, we've got 2, 4, 6, and 8. So the double bond is actually shorter than a single bond because they're sharing twice as many electrons. So you have to be closer to share those electrons. The distance for the length of an oxygen double bond is 121 picometers, which is times 10 to the 12? Times 10 to the negative 12? For a single bond, it's just a little bit longer at 148. Yeah, because nanometers times 10 to the negative 9. This is 121 picometers would be 1.21 meter, or 1.21 times 10 to the negative 12 meters. So talking about very, very tiny distances, but double bonds are shorter than single bonds. All right, so what about nitrogen? Because nitrogen is again in here. So it's going to be a diatomic. I guess it's on the slide, so I can't really ask. I'll do it anyway. So how is nitrogen going to form, how is each of these nitrogens going to get an octet between the two of them? Three pairs of electrons. Yeah, so 3 electrons from each nitrogen, and then we make the triple bond. So just like a single bond is 2 electrons, a double bond is 4 electrons, a triple bond is 6. 6 electrons. So if a double bond is shorter than a single bond, a triple bond is even shorter. And actually, as these bonds get shorter too, they also get stronger. So distance between nitrogen-nitrogen triple bond, or between nuclei, is 110 picometers, whereas in a double bond it was 124, and it was about 140 in a single bond. Because nitrogen is a diatomic molecule, a very strong triple bond, it's relatively unreactive. So actually use it for a lot of things where we're concerned with stuff reacting with oxygen, which is very reactive. Actually, nitrogen is a really important molecule, or very important atom for fertilizer, but not as N2. They have to break that triple bond and incorporate it with oxygen to make nitrates, but it's a very, very strong bond. So that's why crop rotations were a thing, because you could plant peanuts instead of tobacco, because that was the big crop, and it would put more nitrogen in the soil. And then a guy named Haber-Bosch, maybe it was 2 guys. The Bosch-Haber process was like the first time that we were able to make chemical fertilizers without having to use bacteria. That was only like just over 100 years ago, maybe shorter. Okay, so if we want to write Lewis structures for covalent compounds, they're more complicated than writing Lewis structures for ionic compounds. So they're not tricky. More complicated, but only relatively so. So we want to first write the correct skeletal structure for the molecule. which shows the relative positions. And one of the important things here is that hydrogen is always, or hydrogens are always terminal atoms. Because if you think about it, hydrogen only has one electron. It can only ever form one bond. So it can't ever be bound to two things. So when I say terminal, that means it's on the end. It can't be in the middle of a chain. And then most molecules tend to be symmetrical, especially the ones that we're going to cover. They're all going to be symmetrical. So when a molecule contains several atoms of the same type, those tend to be in terminal positions. Of course, there are exceptions. So if I gave you something like C2H6, using these rules, hydrogen cannot be in the middle. So we have to put carbon, and that's going to be bound to another carbon. And then we would place the hydrogens around the carbons at terminal positions, and then divide those hydrogens evenly between the two carbons. So if we have 2 carbons, 6 hydrogens, 3 hydrogens around each, and then we would draw bonds for all of those as well. So it's symmetrical in that the left and right are mirrors of each other. So once you get your skeletal structure written out, then you want to calculate the number of electrons for the Lewis structure by summing or adding up all of the valence electrons for each atom in the molecule. So for main group elements, aside from helium, we could just use the group number for the periodic table. For ions, you add 1 electron for each negative charge and subtract 1 electron for each positive charge. What that means is if we had something like nitrate, which is NO3 minus, this minus means that we have to add 1 more electron after calculating how many valence electrons the atoms have. So nitrogen has, we have 1 nitrogen times 5 valence electrons. For oxygen, we have 3 oxygens times 6 valence electrons. And then we would add this negative here would be, this would be 5, this would be 18 electrons. And we would add 1 more electron because of that negative. So that's what that last slide means. When we have ions like this, if it's a negative charge, then you add 1 electron. If it's a positive charge on the ion, then we subtract 1. After that, you distribute the electrons among the atoms, giving octets to as many atoms as possible. And then you begin by placing 2 electrons between each pair of atoms as the bonds. Those are the minimal number of bonding electrons. And then you distribute the remaining electrons first to terminal atoms, and then to the central atom, again giving octets to as many atoms as possible. And this is key for making these easier to solve. It'll be a lot easier if you do the terminal atoms first. I feel like I had nothing. Okay. Then, if anything doesn't have an octet, form double or triple bonds as necessary to give them octets. So you would take a lone electron pair from a terminal atom into the bonding region, so move that pair between the central atom and that terminal atom to create those multi-bonds, double or triple. Okay. Examples. So first step here is to write out a skeletal structure. So we have one carbon, we have one oxygen. That makes it really easy because they're just going to be next to each other. Don't have to figure out what's going to be a central atom, don't have to figure out terminal atoms. They're both technically terminal atoms. So if carbon and oxygen, this doesn't really matter if they're carbons on the left, oxygens on the right, flipped, or if you went one on top of the other or one below the other, all valid. So this is our skeletal structure. Actually, let me do it this way. This is the oh, it looks so weird. Okay, skeletal structure. Now we need to count how many valence electrons we have total. So how many valence electrons does carbon have? 4. And let me write this out. So we have 4 electrons from carbon, and then from oxygen, 6. So we add those together for a total of 10 valence electrons. Write this as valence electrons. So now we're going to take electrons and we're going to put the minimal number of bonds into our skeletal structure. So that's going to be one bond or one pair of electrons between each of the atoms. Because if there's not a bond between them, they're not part of a molecule. So now, after using 2 electrons to form this bond, we have 8 valence electrons left that we can place around the atoms. So I'm going to go up here. So carbon, get back to oxygen. And we place those 2 at a time. So it's kind of like dealing cards. You're dealing 2 electrons, 2 cards at a time. So we go 1, 2, 3, 4, 5, 6, 7, 8. And if we had a central atom and terminal atoms, we would do the terminal atoms first. In this case, we have only terminal atoms. So this is like a partial Lewis structure. Because we're not done yet. So how many valence electrons does each of these, the carbon and the oxygen, have? 6. Just 6 each. We go 2, not the eraser, 2, 4, and 6. And then for oxygen, it's 2, 4, and 6. So now we can take a lone pair from one of the terminal atoms and move it into the middle. So we'll grab 2 from oxygen here. So move those in, and now we've got a double bond here. And since we took one of those lone pairs from oxygen, it now only has 1 lone pair. Carbon still has those 2. So again, this is a partial Lewis structure again. And so we count again. How many valence electrons does each have? For carbon, 2, 4, 6, 8. Right, so each of those lines counts as 2 electrons. For oxygen, though, it's 2, 4, 6. So what do we do next? Yeah, a lone pair from carbon to make another bond. So we have carbon, triple bond, oxygen. And so we took one lone pair from carbon, so it only has one lone pair, and oxygen only has one lone pair. So if we count these electrons again, it's 2, 4, 6, 8, 2, 4, 6, 8. So that's our Lewis structure.
So essentially, you just keep adding bonds until it balances out.
Mm-hmm. Yeah. And when you do these, well, on the Lewis dot structure worksheet, it has you write out, it does give you some of the steps, and so it says, write out the skeletal structure, then count the number of valence electrons. It's got a spot where you fill in valence electrons. And then you put in your minimum number of bonds, which is one bond between each atom, or at least one bond between the central atom and each atom. And then that's your number of bonding electrons. So in this case, we only had 2 bonding electrons in our skeletal structure. But we did end up with 6 bonding electrons in our Lewis structure. Okay, do more examples. Okay, so now we've got a more complicated molecule. We have carbon, we've got hydrogens, we've got oxygen. This is another rule of thumb. Generally, these formulas are written out in the order of the electrons, more or less. So carbon here is in the middle. Carbon is usually a central atom. And and here it's also written in the middle of the molecular formula. So we're going to put carbon in the middle, and then we'll put the rest of the atoms around carbon. Hydrogen, hydrogen, oxygen. So this is our skeletal structure without bonds. Now, how many valence electrons do we have? Yeah, so there's 2 hydrogens and they have 1 each. We have 1 carbon. That's 4. And then oxygen we have 1 oxygen. 6. So a total of 12. So 12 valence electrons. And then we got to put in our minimum number of bonds. This is where I said minimum number of bonds being 1 bond between each atom and the central atom. So said that to clarify that those are the bonds we need. We don't need a bond between hydrogen and hydrogen and oxygen and oxygen. They just need to be all attached to some part. All right, so how many electrons did we use for bonds? 6, yep. Each of these lines is 2, so 2, 4, 6. So that's our 6. And this is the way it's written on the Lewis dot structure worksheet. Those would be our 6 bonding electrons, at least initial bonding electrons. So we subtract those from our total number of valence electrons. And that means we have 6 more electrons that we need to place. All right, so we should always start placing electrons with the terminal atoms. And we want to fill up those terminal atoms with octets first. So we have 6 electrons. We're going to go 2, 4, 6. Basically, it's a terminal atom if it only has one bond. If it has more than one bond, it's not a terminal atom. It's a central atom. So that's all 2, 4, 6. Those are all of our electrons that we needed to place. But if we count octets, carbon only has 2, 4, 6. Oxygen has 2, 4, 6, 8. So we just take one lone pair from oxygen and form a double bond. And that would be the Lewis structure. So hydrogen only needs a duet, so each of these only has 2 electrons. 2, 4, 6, 8 on carbon, and then 2, 4, 6, and 8 on oxygen. These are, again, another one of those things that I think of in chemistry as a puzzle. And balancing chemical reactions is really just a puzzle. There is a correct solution, just have to find it. Same with Lewis structures. As long as you've counted the correct number of electrons and drawn the skeletal structure correctly, it should work out. Are there any other questions for these Lewis structures? Good? What time is it? 6:05. All right, so for polyatomic ions, like I mentioned nitrate earlier, we follow the same procedure but pay special attention to the charge of the ion when calculating the number of electrons for the Lewis structure. So for every each negative charge, we add 1 electron, and for each positive charge, we subtract 1 electron from our total pool of electrons. And then for Lewis structures of ions, polyatomic ions specifically, we would write out I'm not going to bother to actually fill this in, but so it would be the Lewis structure inside of there with however many electrons need to go around that. I'm sure we'll do nitrate as an example. And then brackets, and then the charge on the outside of that. Ooh, cyanide. Nice. Okay, so again, we do our structural or skeletal first. So carbon, nitrogen. Or better nitrogen. Now, how many valence electrons do we have? 5. And then we also have a minus charge. So we add an extra electron here. So well, I won't put a minus there. So an extra 1 electron for, write this, 1. So our total number of electrons then is 10. So again, negative charges, we add an electron. Okay. Minimum number of bonds, like so. Yeah, so we used 2 of those up. So we got 8 electrons left. And because here we don't have, both of these are terminal atoms, right? Each only has 1 bond at this point. We can just deal those electrons out in pairs. So we have 8, so we'll go 2, 4, 6, 8. And again, we find ourselves in a situation where we need to get more electrons on both. So you first share a pair from carbon, which will give us a double bond. But then, yeah, we're going to need to share another pair here. We'll grab one from nitrogen. So that would be our Lewis structure. brackets, and a negative charge. Yeah. Mm-hmm. Yeah. So we're carrying on the fact that this has an overall negative charge. Because if we were to count up the total number of all the electrons, the number of protons, we'd have one more electron than we have protons. Cool. But hypochlorite. Again, we just start with a skeletal structure, chlorine and oxygen. Chlorine has 7 electrons. Oxygen has 6 electrons. Then we have a negative charge, so do we add 1 electron or subtract 1 electron? Add it. So we're going to have a total of 14 electrons. We're going to go for our minimum number of bonds, which is just 1 bond. Subtract 2 electrons from the total. So 12 electrons to place. And again, because these are both terminal, we'll distribute it in pairs to both of them, our remaining 12. 2, 4, 6, 8, 10, 12. Sometimes you don't need double bonds. You've got to be really sure that you didn't add any extra electrons on accident. You can go through and count all of these and make sure it lines up with your total number of valence electrons. 2, 4, 6, 8, 10, 12, 14. And everything's got an octet. Also, you can tell that if we didn't have that negative charge, we wouldn't be able to have everything with an octet. Right? We'd be missing one of these electrons, wherever it might come from. So then oxygen would only have 7 valence electrons, or chlorine would only have 7. And there would be no way to get them both to 8. Which brings us to this exception to the octet rule. So it's impossible to write good Lewis structures for molecules with odd numbers of electrons, because you can't have all the pairs. So there are molecules that do have odd numbers. And in those cases, you just write the best Lewis structure possible. So, nitrogen monoxide. And we mentioned this one earlier, an exception to the octet rule is boron, also aluminum, which will only have 6 electrons around boron rather than 8. So you can see we only got 2, 4, 6. Now, they do write them out with dots here. Please use lines. It's cleaner. There are some other compounds, if you have deep enough shells. So like sulfur and phosphorus can have larger than 8 electrons, or more than 8 electrons around a central atom in their Lewis structure. They're called expanded octets. So the Lewis structures aren't perfect for everything, but they explain most things, and there are a few exceptions that you'll have to do more chemistry to learn about. Oh yeah. This is just like touching very briefly on some almost organic chemistry. So there's some structures or some molecules like sulfur. So if we write out a Lewis structure for sulfur, end up with sulfur, 2 oxygens. Then oxygen has, so 2 times 6 electrons. Sulfur is 1 times 6 electrons. So we got a total of 18 electrons there. I'm just going to do this real fast. So then we can do 2 bonds, which leaves us with 14 left to place. We'll do it like this. 2, not 4, 2. Like that, so we got 14 left. So we go terminal atoms first. 2, 4, 6, 8, 10, 12, 14. So for sulfur dioxide, we need to form 1 double bond to get sulfur an octet. But it doesn't matter which oxygen it comes from. So we take a lone pair from this oxygen and move it in, and that would give us this. Or we could have taken a lone pair, do it in a different color, from here to make this. Now, if you think about it, you could really just take one and flip it, and it becomes the other. In reality, it's not one or the other. It's actually a hybrid of the two. So instead of having 2 full double bonds, you have like 2 partial, like 1.5 bonds. So these are called resonance structures. So both of these are valid. You'd usually write them a little further apart, and then you would put a line between it to say it's both of these. So like I explained sort of briefly, either one of the 2 Lewis structures for SO2 predicts that SO2 would have 2 different kinds of bonds, 1 double and 1 single. But in reality, if we examine these, we find that it's a hybrid of a double and single bond. So that's Chem 1 stuff. If you take, Chem 1A. So those bonds are also equivalent. So if you were to measure the length of the bonds, remember we talked about a single bond's like 140, and a double bond is like 140, 120? The length of each of those bonds would be like 130. So it'd be halfway in between a single bond and a double bond. And the strength as well. So you can write these out, like this. We're just using an arrow to show that it could be one or the other. But it's truly, in reality. The other way you can write this out is if you do sulfur, and then you have, actually, this will get weird with the number of electrons. So you draw one of those bonds with dashed lines. But then it gets a little bit difficult to count where those electrons are. All right, so let's do nitrate and include resonance structures. So which atom is going to be our central atom? Nitrogen. If we have multiple atoms, those will be the terminal ones. So nitrogen. You can draw those bonds in, but I think it helps to wait and put them in because it makes it easier for the counting of electrons. All right, so we have nitrogen, 5 electrons, oxygen, 6 electrons. So this one's times 2. So 12, 5, and then we have another negative charge. So we're going to add one more there. I did not give myself enough space. And pretty much you'll always find that if you have nitrogen involved, nitrogen has 5 valence electrons, so there's always going to have to be some kind of charge involved with nitrogen. So that'll give us 18 valence electrons. Our minimum number of bonds is going to give us 2 bonds. So that's 4 electrons that we subtract. I got 14 electrons left over. And again, we're going to start on the terminal atoms, fill those up first, and then move to the central atom. So 2, 4, 6, 8, 10, 12, and then 14. So now I have to take one lone pair. From it, taking the lone pair from the terminal atom to form a double bond. So that's 1. And then our other resonance structure would result from just doing the same thing on the other side. Any questions? Yeah.
So I have a question. On the oxygen, I know we took the 2 electrons and then we created a double bond between oxygen and nitrogen.
Mm-hmm.
Can you explain to me like why we did that? Because I counted the valence electrons on just oxygen, that's 2, 4, 6, and then 8 including the bond. So that would be stable, right? But we created a double bond.
The oxygen's stable, but how many valence electrons does nitrogen have?
Oh, okay.
Yeah.
I see. So it has to have 8 as well, right?
Mm-hmm. Yeah. So everything will have 8, unless it's hydrogen, then it'll have 2, or boron or aluminum, they can have 6.
Okay.
But everything else, yeah. Any other questions? Practice. Oh yeah. Yeah, that's a good stopping point. So next week we'll talk about why or how the electrons are important for predicting the shapes that atoms are. Ooh.